In this example, we're given the function f of x equals x squared times e raised to the power of 4x and asked to determine the open intervals where the function is concave up or concave down, and also determine any points of inflection. So here, because we're talking about concavity and points of inflection, we'll be working with the second derivative of the given function, where any possible points of inflection will occur where the second derivative is equal to 0 or undefined. And over an interval, if the second derivative is positive, the function is concave up. And if the second derivative is negative over an interval, the function is concave down. So we want to find the second derivative, but before we find the second derivative, we must first find the first derivative. And looking at the function f of x, notice how we'll have to apply the product rule in order to find the first derivative. So applying the product rule, f prime of x is equal to the first function, which will let be x squared, times the derivative of the second function, which would be the derivative of e to the 4x, and then we'd have plus the second function of e raised to the power of 4x times the derivative of the first function, which would be the derivative of x squared. Which means f prime of x is equal to x squared times, now to find the derivative of e to the 4x, we'll have to apply the chain rule. So the derivative of e to the 4x would be e to the 4x times the derivative of 4x, which is 4. So our derivative would be 4 e to the 4x. And then we have plus e to the 4x times the derivative of x squared, that's 2x. And now we'll simplify. F prime of x is equal to, here we'd have 4x squared e to the 4x plus 2x e to the 4x. So this is the first derivative, but remember our goal is to find the second derivative and determine where it's undefined or equal to 0. In order to find the second derivative, notice how we'll have to apply the product rule to find the derivative of the first term, and then the product rule again to find the derivative of the second term. And let's do this on the next slide. So f double prime of x is going to be equal to, for the derivative of the first term, we'd have the first function 4x squared times the derivative of the second function, which is derivative of e to the 4x, plus the second function of e to the 4x times the derivative of the first function, which would be 4x squared. So this gives us the derivative of the first term, and now we need to find the derivative of the second term, which would be 2x times the derivative of e to the 4x, the second function, plus the second function of e to the 4x times the derivative of the first function, which is 2x. So f double prime of x is equal to 4x squared times the derivative of e to the 4x, which is 4 e to the 4x. Then we have plus e to the 4x times the derivative of 4x squared, that'd be 8x, so times 8x plus 2x times the derivative of e to the 4x, which is 4 e to the 4x, and then plus e to the 4x times derivative of 2x, which is 2. And now we'll find these products. So we have f double prime of x equals, here we're going to have 16x squared e to the 4x, plus here we have 8x e to the 4x, plus here we have another 8x e to the 4x, and plus 2 e to the 4x. But notice how we do have two like terms here, so we'll go ahead and combine those. So we have f double prime of x equals 16x squared e to the 4x plus 16x e to the 4x plus 2 e to the 4x. Now we want to determine where the second derivative is going to be undefined or equal to 0. Notice how it will never be undefined, so we'll set this equal to 0 and solve for x. And again, the solutions will give us the locations of possible points of inflection. And let's go ahead and do this on the next slide. So now we'll set this equal to 0 and solve. And we'll start by factoring. Notice how the greatest common factor of the three terms would be 2 e to the 4x. So if we factor out 2 e to the 4x, we'd be left with 8x squared, and then plus 8x, and then plus 1. Of course, we can distribute if we want to check. So this product would be equal to 0 when 2 e to the 4x equals 0, or when 8x squared plus 8x plus 1 equals 0. Well, notice how 2 e to the 4x is never going to be 0, and therefore we'll only get solutions by solving this quadratic equation here, which unfortunately does not factor. And therefore we'll have to apply the quadratic formula where a equals 8, b equals 8, and c equals 1. And the quadratic formula is given here below for reference. So solving for x, we would have x equals negative b, which would be negative 8, plus or minus the square root of b squared, that'd be 8 squared, minus 4 times a, which is 8, times c, which is 1, all over 2 times a, or 2 times 8. So simplifying, we'd have negative 8, plus or minus the square root of, this is going to be 64 minus 32, which is 32, divided by 16. And now we can simplify the square root of 32. Remember, the square root of 32 is equal to the square root of 16 times 2, which simplifies to 4 square root 2, since the square root of 16 is equal to 4. So now we have x equals negative 8 plus or minus 4 square root 2 divided by 16. To simplify this, let's break it up into two separate fractions. We'd have negative 8/16 plus or minus 4 square root 2 over 16, which would be negative 1/2 plus or minus, and here we'd have square root 2 divided by 4. So the two locations of possible points of inflection would be x equals negative 1/2 minus square root 2 divided by 4. And then the other x value would be x equals negative 1/2 plus square root 2 divided by 4. So now we're going to divide the domain of the original function, which is all real numbers, into 3 intervals using these x values. When we do this, though, it'll be helpful to have decimal approximations. So negative 1/2 minus square root 2 divided by 4 is approximately negative 0.8536. And negative 1/2 plus square root 2 divided by 4 is approximately negative 0.1464. And to save some time, I've already set this up in a table. And notice how I included both the exact values of x as well as the decimal approximations. So looking at the approximations, the first interval is from negative infinity to approximately negative 0.8536. The next interval is from negative 0.8536 to negative 0.1464. The third interval is from negative 0.1464 to positive infinity. And now we'll pick test values in each interval. For this first interval, let's use negative 1. For this interval here, let's use, let's say, negative 0.5. And for this interval, let's use 1. Now we're going to test the sign of the second derivative at each of these test values. And the sign of the second derivative will tell us whether the function is concave up or concave down over the given interval. And we'll do this using the graphing calculator to save some time. And I've already entered the function and the second derivative into y1 and y2, which we see here. So now we'll use a table feature to check the sign of the second derivative at these test values, which remember is in y2. Before we go to the table, though, let's check our table set by pressing second window. We want to make sure the independent variable is on ask. And it already is, so we'll press second graph. And I've already typed in the test values, and the way I did this was I just entered negative 1, enter, negative 0.5, enter, and 1, enter. And remember, the second derivative is in y2, so at x equals negative 1, the second derivative is positive. At negative 0.5, it's negative, and at positive 1, it's positive. So the signs are positive, negative, positive, which means over this first interval, the function is concave up because the second derivative is positive. Here, the second derivative is negative, so the function is concave down over this entire interval. And on the right, the second derivative is positive, so again, the function is concave up over the entire interval. So notice how this tells us we do have a point of inflection here at approximately negative 0.8536 because the function changes concavity at that location, and also it changes concavity at approximately negative 0.1464. So to finish the problem, we'll list the points of inflection. And we'll go and just use the decimal approximations for the points of inflection. So for the first point of inflection, the x-coordinate is approximately negative 0.8536. We'll have to evaluate the original function to determine the y-coordinate of this first point of inflection. The second point of inflection has an x-coordinate of approximately negative 0.1464. And again, we'll have to evaluate the function at this x value to determine the y-coordinate. And let's go ahead and do this using the graphing calculator. So using the table now, we'll enter the x value of negative 0.8536. Enter. Remember, the original function is in y1, so the approximate y-coordinate, if we move the cursor over to y1, we can see more decimal places down here below. To 4 decimal places, this is round to 0.0240, because the 6 indicates to round up, so approximately 0.0240. So 0.0240 as the approximation of the y-coordinate of the first point of inflection. And now for the second point of inflection, we'll press down and then right back to the next x value. We'll enter negative 0.1464. Enter. And again, we'll go ahead and move the cursor over to y1 so we can see more decimal places here. The y-coordinate will be approximately 0.0119. Of course, if we entered the exact x values rather than decimal approximations, we would have more accuracy. But for this problem, the decimal approximations work just fine. I hope you found this helpful.